And we are live. So, a warm welcome to each and everyone. Thank you so much for tuning in and joining us today for our new session of Let Us Talk It Zipiners. So, my name is Phil. I'll be your host today. And we are live on YouTube, on Twitch, and on Facebook as well. And if you'd love to interact with our speaker, you can join in our live Zoom meetings. All right. And yeah, we are bringing you today a wonderful topic. Just like the previous Wednesday that we have great speakers and we have great topics. And today we have a different topic that we'll be bringing you. But before that, this initiative is made possible by Cogent Integrated Business Solutions. So they wanted to give back to the community and they wanted it in a form of knowledge. So they created this free knowledge sharing platform as we believe that knowledge should be free and not just information that we share here. We also share the personal and exceptional experiences of our professional guest speakers, seasoned professionals, that they share their experiences and their top of the line work into this platform, and especially their most valuable time and effort, and that we appreciate. All right. So, the first topic, or I mean, the topic that we'll be discussing today is about genesis of AI and the meteoric rise of transformers. And definitely, this is an interesting topic because uh, the guest speaker that we have today written a book that includes this topic that we have today, but this is just a drop of that book, which you will learn a lot of things. And this talk is actually partitioned into two segments. So we have the first one, which our speaker will discuss about the genesis of AI and how it went through to boom bust cycle during the 1960s and 1990s. And in the second segment, our speaker will discuss recent successes and shortcomings of deep learning networks, which includes generative pre-trained transformers and large language models. Also, our speaker will discuss a few novel and unique use cases where AI is being used or will be used soon, and they're helpful in these are helpful in comprehending the depth and breadth of AI's brain explosion. And our guest speaker is none other than Dr. Alok Agarwal, CEO of Scry AI, and has received his bachelor's in technology from the Indian Institute of Technology in Delhi in 1980. And in 1984, he received his PhD in electrical engineering and computer science from Johns Hopkins University and worked at IBM's TJ Watson Research Center in New York between 1984 and 2000. And much of the accomplishments that he has accumulated, and he will be sharing with us later on about his book and where to get it. But before that, let's welcome Sir Alok Agarwal. How are you doing today, sir?
Good. Thank you for having me, Phil. Doing well. How are you?
I'm doing great. Thank you so much for asking, Dr. Alok. And today, what inspired you to choose this topic that you will be sharing with us today?
Yeah, so the reason I wrote the book is pretty much the reason why you have Cogent, which is that knowledge is the biggest asset we humans have, and we should be sharing pretty much at no cost with people who need knowledge and who need to understand things. So originally, I had written four chapters or four articles in 2018, which some of the professors started using them in their courses in MBA schools and Master of Business Analytics. That prompted me to start the book, writing the book in January 2021, and I finally finished and it got published in December 2023. The title of the book is The Fourth Industrial Revolution and 100 Years of AI, 1950 to 2050. And it's available on Amazon in a Kindle version and also in paperback and in hard copy. And very soon will be available in Audible. And in Q4 of this year, 36 lectures, video lectures, will be available from these 17 chapters, each lecture being about 45 minutes each. And this particular topic that I'll be covering comes from two chapters, namely chapter 2 and chapter 11. And I think it is important because we are going through another hype cycle of GPTs and LLMs. Not a day goes by when somebody hasn't introduced another LLM. Not a day goes by when at least 1,000 people on LinkedIn haven't told how they're using LLMs. But life is not that simple. And we have, as you rightly said, we've already gone through two hype cycles in AI, one in 1960s and 70s, the other in late 1980s and early 1990s. And I think some of the lessons learned from there should not be lost. That's part of the reason to discuss genesis of AI and also the meteoric rise of transformers, wherein in transformers or LLMs, I'll be talking less about applications, and more about their limitations, because I think that is what makes more sense, since a lot of people already have played with transformers and generative AI in general, as well as LLMs.
All right, that would be fantastic, sir. That's a great initiative, and that's very thoughtful in terms of the publication of the book to share the information that you have gathered throughout your experience. So we are excited to hear more of what you have decided to share with us today and the topic as well. So please carry on, Dr. Agarwal.
Oh, thank you. Thank you. So, okay. So starting from 1950, let's go back in history a bit. How did the whole thing start? Alan Turing was a very well-known mathematician by 1950. In fact, he had helped the Allies win the war against Germany, Italy, and Japan by decoding some of the important codes that were coming from Germany, and probably saved thousands of lives in the whole process. So he was very well known already. In 1950, after the war was over, in 1950 October, he wrote a paper which basically began to be called the imitation game. The paper basically asked the following question. Suppose there is a computer sitting in one room. Let's not forget it's 1950, so we did not even have semiconductors at that time. All the computers which only came out, electronic numerical integrated computer came out in 1945, and it was made of valves or vacuum tubes. We'll talk about vacuum tubes in a minute. But suppose there is a computer in one room and talking to a judge via printed material or via cables. There is a man sitting in another room. Judge is asking questions from both of them. Can the computer imitate the man so as the judge is confused and he begins to think, or she begins to think of the computer? So that was the imitation game. There is a movie made after Alan Turing. I would highly recommend it. It's about his bio picture, and it ends in the imitation game. So in 1952, there was an interesting interview that BBC, British Broadcasting Company, held, and they asked two very interesting questions. First question was, when do you think such computers would be even available? And he says, in my opinion, not for another 100 years. And of course, 100 years means 2052. In another roughly 28 years will be there. The second question they asked was equally interesting, which was, how do you think such computers will be created? And he said, just like we train human children, we teach them, then we test them, we need to train these computers in a similar way, which he called them as child machines. And this is, his insight was so deep that if you look at it today, we do train most of our computers using supervised machine learning, which is pretty much how we train our children. We tell a child 1 + 1 = 2, 2 + 2 = 4, and it give the reasons why, or just explain it, and then ask questions, which is validate and test by testing on an exam or testing on a quiz, etc. And that is precisely what we following supervised machine learning, which we'll talk about in a few minutes. Again, because of this deep insights that he has, Alan Turing is often called the father of artificial intelligence. And in fact, the book is dedicated to him. While he was doing this, he was not alone. There was a graduate student at California Institute of Technology, Marvin Minsky, along with a good friend of his, Pete Edmonds. They built a interesting, interesting model, simulated an interesting model of a rat who was able to find a cheese in a 4x4 maze. So again, there were no semiconductors. What you're seeing is the particular model was called SNARC, Stochastic Neural and Analog Reinforcement Calculator, and it had 300 units of the kind that you're seeing there. Interestingly, these are vacuum tubes or valves, and they're nothing different than bulbs, very similar to bulbs, except to make sure that they don't fuse as often as bulbs, the air has been taken out of it so they don't oxidize and therefore they fuse less, but they still fused a lot. In fact, because they were like bulbs, there is a filament inside each of these vacuum tubes, and that will attract moths and flies in ENIAC in the computer, which will come to the vacuum tube, they will get burned, they'll die, and then they will short circuit the entire system. That's why once a system is shorted, then obviously somebody has to fix it. That's why the word bug came about. Just an interesting piece of history, which we call software bugs. It all started with hardware bugs, which all started because Grace Hopper and Harvard actually find one of the bugs which actually died and which had short-circuited ENIAC, the first calculator. Anyway, moving back to AI, the name AI was given by John McCarthy. He was a professor, young professor at Dartmouth. In 1955, he wrote a proposal to National Science Foundation that he wanted to hold a conference in 1956 and get 10 researchers. Unfortunately, by that time, Alan Turing had died. I won't go into his death. You can again watch Imitation Game. He wanted 10 to 12 people to come to the conference and discuss what they were doing, including Marvin Minsky and others. And the whole aim of the NSF proposal was to explore ways to make a machine that could reason like human, was capable of abstract thought, problem solving, and self-improvement. So with that, the NSF, the proposal was accepted, and there were these 10 people who were the pioneers of AI. And in this particular proposal, he coined the term artificial intelligence. Some of them were, of course, Marvin Minsky, Arthur Samuel, we'll talk about, and then there were many others. So it was 1955 proposal that coined the term artificial intelligence. And that is how, and it is during this conference that AI gained its vision, mission, and hype. The good thing about hype, as you'll see, I'll talk a lot about hype and boom bust cycles. The good thing about hype, just like what we are seeing today, is everyone gets extremely excited. You have a lot of passion, grit, and amongst inventors, and that produces a lot of good results. For example, even though this hype was amongst researchers at that time, pretty much all the areas, basic areas, fundamental areas of AI were actually defined in a very, very proper way during 1950s and 60s, which include supervised machine learning, unsupervised machine learning, reinforcement learning, theoretical aspects of machine learning, natural language processing, speech audio processing, expert systems, video and image processing, and other intelligent actions. They were all effectively developed during this period. So one of the big advantages when people get excited. And in the whole process, there was a revolution that took place. A revolution is when you change a paradigm completely. So an industrial revolution is where you have new things which will literally change the entire society. The social revolutions, when you go from, for example, from democracy or capitalism to communism or socialism. So here are different kind of a revolution occurring. And because of this revolution, a new field called computer science came about. Before that, computer science was just part of math or electrical engineering. In fact, in many universities, even till today, electrical engineering and computer science is one department. For example, University of California, Berkeley, or MIT. So what was this revolution about? Before Alan Turing and before AI was coined, the notion of an algorithm is a set of rules for solving a problem. For example, if you ask me how to add n numbers, I would say in the ith step, take the sum which has been produced in the previous step of first I minus one number and add the ith number to it. So now you have the sum of the first I numbers in the I plus first step. Take the sum which have been added, which has already been added, which is S sub I, or sum of I numbers, add the I plus first number to it. That's an algorithm. It's well defined. It does not change with time. It does not change with the data that you give in. More data doesn't change it. Time doesn't change it. And this process has been used since Egyptians' time. They were using geometric algorithms for measuring how much how much area to put seeds in and put water in and so on from Nile River. And the first person who formalized this was Muhammad al-Khwarizmi, who is considered as father of algebra because he gave the algorithm or the way of solving quadratic equations and linear equations. And his last name was al-Khwarizmi. It became algorithmy in Latin and then became algorithm in English. And that's how the word algorithm came about. As I said, these traditional algorithms are fixed. They do not change over time or after processing data. This paradigm of traditional algorithms differs from the way humans solve problems because humans learn and change their rules over time. Hence, the pioneers realized that these machines would also need to learn and modify their algorithms, their inside algorithms, by just like humans. Arthur Samuel, who was one of the people who attended that conference in 1959, he joined IBM Research when it was just formed. He gave this particular thing and defined machine learning as a field of study that gives the computers the ability to learn without being explicitly programmed. So unlike what we discussed as sum of fine numbers, here the computer should be allowed to learn without being told how to learn. And that is, again, going back to child machines, very similar idea as Alan Turing had. So if we look at supervised machine learning or child machines, here is an example to explain it. Suppose we were given 1 million pictures of faces of dogs and cats. And I was asked to separate it into faces of dogs and another group into faces of cats. I could do two ways. I can give it to a 5-year-old or 8-year-old and say, look, why don't you do it? And the guy would say dog, 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 cat, 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 etc., etc. Take probably quite a few days to doing it. Another way is I, as a computer scientist, may write an algorithm, and I'll call it a black box algorithm for the time. We'll talk about this a bit more later. And let's say Phil is a subject matter expert who has studied faces of dogs and cats a lot. And I'll sit with him. I said, Phil, you have the subject matter expertise. Why don't you tell me what differentiates faces of dogs and cats? And he says, well, cats have whiskers, dogs have droopy ears, the noses are different. Cats have more rounded faces, dogs typically have more triangular or angular faces, and so on. I take those features and put it in the system and write an algorithm which is now we'll call a black box. The child has, let's say, only labeled the first 10,000 pictures as dogs and cats. The first picture comes in, it's a picture of cat that the child has given. The system outputs and it says it's a cat. If there is no error, it is a cat, the child has said it's a cat, or the labeler has said it's a cat, there is no error, it doesn't change itself. Next one comes in. It's a picture of a dog, but the system says it's a cat. Then this error is fed back. The error is fed back, and the black box changes its something internally, and so that the input, which was originally, it was saying that output was a dog, it becomes a cat. So it has modified its internal working so that the output becomes. Similarly, next one comes in again. It's let's say it's a dog. It says it's a cat. Then it changes. It's in, and if it continues changing, and if there were enough features that Phil gave me and that I incorporated into the black box algorithm, machine learning algorithm, after 10,000 or so pictures, it would become reasonably accurate. Maybe with 80% accuracy, it will be able to differentiate between cats and dogs. Humans are able to differentiate between cats and dogs to 99% accuracy or higher if the pixelation or if the quality of the pictures are good. Yeah. So that's what supervised machine learning is. Now, just very briefly, what happens inside these black boxes? There are many algorithms. One of the algorithms is called are basically artificial neural networks. They were originally called perceptrons. In 1958, Rosenblatt gave the first perceptron, or the first artificial neural network. It was based on the idea of human neurons, or those in rats and mice, or those in squirrels. And take most of the living beings or animals, you'll find these. Fish, for example. A neuron, which is shown at a very schematic level at the above, is a cell body. It's connected to the neurons coming from the other side, on the left side, left top, and it's connected on the right side through other neurons through these connections, which go to the right side of the neurons. And neurons have an advantage or have a property that that there is no forward, backward. Things can move in both directions, and signals can move in both directions. How do these actual neurons work? If these neurons it's connected to have enough signal or enough voltage or enough level in them, depending on their strength, they would multiply by their strength and send the signal multiplied by its strength into this neuron. It will sum up all the strengths times signal for each of the neurons that is coming in. And if the sum is above a threshold, then it will fire and send the signal back. And again, it has a strength, so it will get, when it sends it, it will get connected with that strength. So the whole idea of perceptrons at that time, or artificial neural networks, is input is coming in. Each of these edges have a weight or a strength associated, multiplied by the input. So this multiplies by this input, weight on this edge or strength on this multiplied by this, and so on. If it exceeds the threshold, then it will send the signals out. Remember, again, it's 1958. They did not have any semiconductors. We were working with vacuum tubes or valves, and therefore all he could do was create basically three levels. One were taking inputs, one was an output neuron, artificial neuron, and there was a middle layer. And later on, these particular perceptrons or artificial neural networks began to be called as shallow networks. They had only one layer in the middle. Because there was only one layer in the middle, it had a lot of limitations that it could do. This is 1958. Russians, part of Soviet Union, were already looking at what was happening in the US. They actually, at a theoretical level, they already extended it to 8 levels in the middle. So rather than having one level, they actually extended to as many levels as you can have, and they call them multi-level or multi-layer perceptrons. So there were many layers. They also, at that time, again, we did not have 0 ones because it was all electricity in a sinusoidal wave. So you had analog functions, and just like humans or mice or rats, these particular signals could go back and forth. So they already gave multi-layered perceptrons. They translated their manuscript in Russian into English in 1966, thanks to Purdue University. But still, most of us forgot. I mean, the West forgot about what they had done, and later on rediscovered them as deep learning networks. which we'll discuss in a few. There was another thing which was interesting, and this is particularly useful for our discussion. It was chatterbots or chatbots. So Professor Weizenbaum, who was at MIT, who was a professor at MIT, he decided to use one of these computers in 1966 and train it so as to talk to him, chat with him in English. He called the computer Eliza, and that name came from My Fair Lady. If you've seen the movie, you'll remember Professor Higgins is trying to teach Eliza Doolittle, a flower girl, to speak such perfect English that nobody can recognize her from royalty. And that's why he called it Eliza. Of course, his training, he realized very soon in 1970s that training on chatbots is a very, very hard problem. Here is an example of what happened. The student will go and say, hello, it'll say, hello, I'm Eliza. The student will say, I'm afraid. Eliza says, how long have you been afraid? Since midterms. Tell me more. I'm afraid that I'll fail in midterms. I'll fail my course. Do you enjoy being afraid that you will fail in your course? Now, this is this is essentially no knowledge, zero knowledge conversation, right? I mean, they're just saying, Eliza is saying this for the sake of saying it. So, but the interesting part was that even though Eliza was very rudimentary, Professor Weizenbaum's secretary began to like Eliza so much and began to confide in her. So she would often say, Professor Weizenbaum, can you please leave the room? I need to talk to Eliza. And she would basically pour her heart out, telling various things to Eliza, even though Eliza would not understand. It wasn't only her. Many students and staff members of Professor Weizenbaum had thought that Eliza was somehow sentient, even though Eliza was making meaningless talk. Yeah. So this was the time when, again, these inventors were extremely excited, extremely passionate. They had the grit to achieve what they wanted to achieve, and hence started the hype. For example, in 1967, Marvin Minsky, who was one of the chief architects of AI in those days, said, within our lifetime, machines may surpass in general intelligence. You hear these words, artificial general intelligence, all the time. Somebody or the other is talking about artificial general intelligence. It's not the first time. It was so strong that actually even the movie came out. And if you haven't seen the movie, I would again recommend another movie to you, 2001 Space Odyssey, which was based on a novel by Arthur C. Clarke, who was a sci-fi writer, a science fiction writer, in which this particular thing that you're seeing, this eye is the eye of the computer behind, who's HAL 9000, who's shown to basically, and the reason it's 2001 is that these pioneers believe that by 2000, pretty much all problems that humans can solve will be solved by computers. They will have emotions. They will be artificially general intelligent computers with emotions, humors. And indeed, HAL 9000 in this movie is shown to be somebody like that, who has a sense of humor, who has emotions, who is arrogant, doesn't think he can ever go wrong or it can ever go wrong. In fact, it makes a mistake, and when an astronaut tells him that you're making a mistake, you've made a mistake, he said, HAL 9000 series never makes a mistake. It can only be attributable to human error. So that was the kind of hype that was created, and it went bust in 1970s when all these researchers realized that getting to human level intelligence, even to solve the imitation game, is a very hard problem. In fact, somebody asked Professor John McCarthy, who gave a reporter from New York Times asked Professor John McCarthy as to when do you think we'll get it in 1977 after the hype has gone down? And he said, not for it'll happen, but for this we need 1.7 Einsteins and 0.3 Manhattan projects. And probably if you have seen the movie Oppenheimer, you already know about the Manhattan project. And what he was trying to say is we need another revolution in the system. So since then, what has happened? I will skip the second a second winter or the second hype which happened in 1980s and went bust in late 1980s, early 1990s. One of the biggest things that happened was that Moore's law came into effect. Gordon Moore, who was one of the co-founders of Intel, uh, gave a law, basically a statement, an observation in 1965, and semiconductors had just come out. And the statement was that in every year, the size of a chip or a transistor, which is the building block, would go down by half every year, which means the cost will also go down by approximately half, which means in 10 years, it will go down by a factor of 2 to the 10, which is about 1,000. He changed it in 1975 that he revises that going forward, it will go down by half every 2 years. And this law has been pretty much there from 1975 to now. But after 2025, we will be reaching the level of atoms, and there will be a lot of quantum effects which will stop this law from going forward. And Dr. Moore, about 7 or 8 years ago, actually himself said, I can see the demise of Moore's law. He himself passed away a few months ago, and the demise of Moore's law is imminent in the next 2 to 3 years, maybe 5 years. But because of this, you see, first 10 years it went up by 2 to the 10. Now you another 1975 to 2025, you have 25 years, so it has gone up another 32 million times. So you have a very, very big improvement in how small the computers, how small the transistors can be, and therefore how cheap the computers can. And therefore, now you can have, instead of one layer, you can have many layers in between the input and output. And it's the weights, by the way, on these between the edges, it's the weights which are the signals, as I was talking about, which are changed by the system when it's told it's not a cat but a dog. It changes the weights to make it the output to be a dog instead of a cat. And these, why are they called deep learning networks? It's the depth of the number of hidden layers in it. So this is a deep learning network with depth 2. If there was another layer in the middle, it will become depth 3 and so on. It's not deep learning networks because they think deeply. In fact, we do not know how they think, but it's a deep learning network because the depth is 2. Yeah. So Ivakhenko and Lapa's vision, which was given in 1965 as multi-layered perceptrons, had finally come true in late 1980s, early 1990s. Since then, a lot of modifications, a lot of improvements have happened. I will not go into it. Let me move on to generative AI. Because of all these deep learning networks, in 2014, the first paper came out, Generative Adversarial Networks, and then another one on stable diffusion. And what they were able to do was these particular networks, which are all deep learning networks, what they were able to do was to basically learn effectively paintings from Picasso or paintings from other artists and create new paintings by combining them. For example, Jason Allen used one of the generative AI systems, Midjourney, to create this painting. And you see, this painting is kind of interesting. Portion of it is classical and opera going on, and then in the background is something out of the world, perhaps out of this solar system, right? So, and he won an award. Of course, this started a debate as to what is art, and the artist said, look, this is not really art. But then it's not clear if this is not art, then what is art? So this was one of the beginning perspectives of generative AI systems with generative adversarial networks in 2014 and diffusion models in 2016. Interestingly, in 2017, there is a paper came out which began to be the foundation of generative pre-trained transformers. The paper was titled "Attention is All You Need," and Google created the first transformer. Let me try and explain what was the situation before 2018 and how it changed. So most of these deep learning networks and most of the other AI systems were only looking, when they were trying to understand natural language processing, they were only looking at, let's say, if you look at chicken in the first question, why did chicken cross the road? They would only look at adjacent adjacent words, the and cross, or maybe two adjacent words, did the and chicken cross the. What it said is that you should be looking at many more words, and you should then fix the attention where it's most important. So, as an example, suppose you ask me a question, why did chicken cross the road? And I answer, because it wanted to. You would immediately understand that it implied chicken. And see, the difference between chicken and it, distance, is cross the road and because. So 4 letters away. Suppose you asked me, why did chicken cross the road? And I said, because it was easy to cross. You immediately associate it with road. So your attention is immediately on the road. So generative pre-trained transformers at a very top level are deep learning networks, but these are networks where the IX layer is not only connected to the layer before and the layer after, but it's connected to several layers before and several layers after. So for each word, you could have a lot of information about many previous words. For example, it could be easily 100 previous words and 100 following words instead of only 2 or 3. Even humans, by the way, have attention, but they don't go 2 chapters before. I mean, that's why the books often say, please see, when you're chapter 11, it will say, please see section 2.3 for more details, because the author knows that by that time, you might have forgotten what 2.3 was. Yeah. So that's what it is all about. It's all about attention and how many words you want to, for each word that you're looking at, or the deep learning network is looking at, how many words does it want to go back and how many words does it want to go. So these, obviously, you have added so many more edges, and these edges, as we discussed earlier, are the ones which have weights, and therefore you have to train them. So that's why generative pre-trained transformers have usually lots of edges, many more than DLNs, deep learning networks. And deep learning networks, on the other hand, are only looking at 1 or 2 or maximum 3 words before and 3 words later, and therefore they often fail on answering questions related to natural language processing. So, in short, BERT started this whole discussion. BERT was based on that particular paper, Attention is All You Need. It only had 175 million edges. It was trained on reasonable amount of data, but not too much data, about 375 million words of data, roughly speaking. Its accuracy was still not as good, was about 73% on most of the metrics that we tried at Spry AI. But this started a race with OpenAI and Meta and others. And hence, there were, by June 2023, there were already 75 generative pre-trained transformers, not only in language models, not only answering language, but many of them were answering other questions related to videos, to basically pictures, images, and so on and so forth. Yeah. Now you have a lot of many. Now GPT 3.5, for example, had not 175 million, but 175 billion parameters, and trained on 375 billion words. Today, GPT 4.0 and others are effectively being trained on about 3 to 4 trillion words, which is about 1 to 1 billion or 4 billion pages. Yeah. So that's the amount of training that goes into it. That's why they're pretty expensive to train. Let's consider what is happening in human brain. We have 86 billion artificial neurons equivalent. I mean, if we were to take a deep learning network, we'll have to create 86 billion artificial neurons, because human brain and the nervous system has that many real neurons. It has about 1,000 trillion edges, not 175 billion edges, but 1,000 trillion edges. So we are talking about another factor of about 5 1,000 times more. It can store about 250 million gigabytes of data. Yeah. So, and approximately um, uh, and approximately $25 trillion will be spent in training. So what can GPTs do at a very top level? They can, of course, write generic recommendation letters for people. They can write generic poems, generic stories, which are very, very interesting. People are still awed by how well they do, and we'll come to that in a minute. They can answer customer questions to a great extent, offer one-on-one to tutors, and so on and so forth. They can provide some specific company information on individual companies, summarization is a very big aspect of it, and communicate insights with salespeople. Where do they usually fail? They've been trained on textual data by and large. So they fail quite miserably on tables, charts, spreadsheets, and so on. So if you give them a bar chart or a pie chart, they'll fail spectacularly. Similarly, forms, figures, flowcharts. And again, OpenAI and Anthropic and many other companies, Meta, are trying to fix some of these flaws. So that's one of the places. So another place where they so another place where they fail, where DLNs fail, is generally in context. For example, Gary Marcus is a professor at NYU, and he gave the following prompt to a generative transformer and to a deep learning network, which was a generative AI system. A horse riding an astronaut. It's not an astronaut riding a horse riding an astronaut. And invariably, the answer that it created was a picture of astronaut riding. Yeah. So it's a very interesting, they're brittle, they break easily. Here is another example. This author, who is a woman from Carnegie Mellon in 2017, she put in psychedelic glasses and asked a very well-trained deep learning network to recognize. And the deep learning network recognized it as Brad Pitt. As you may know, Brad Pitt is one of the very well-known actors in Hollywood. With 99% confidence, it recognized. She also put some stickers or graffiti on stop signs, and it was not able to understand that it was a stop sign. And this would have massive consequences for driverless cars for obvious reasons. Some other examples from Carnegie Mellon University research paper. Look at what these are, basically random images, right? And the deep learning network said it was king penguin or baseball with a 99%. This continues with transformers, and they begin to hallucinate a lot. For example, we asked GPT 3.5, what is distinctive about the roof of MIT building, Massachusetts Institute of Technology building? And those who have seen it in the pictures or in reality would immediately say that it's a dome, because most universities don't have this kind of a dome. But the answer from ChatGPT was there is nothing distinctive. It's made of glass. So it was hallucinating. MIT is in Boston. Boston is very cold most of the year, eight months or so in the year, or at least 7 months. You cannot really grow grass even on the floor, in the ground easily. Forget about growing grass on the top of a building, the roof of a building. We asked the same question. It said it's made of red clay tiles, which will work awfully because you have so much snow and ice that ice will seep underneath the red clay tiles and basically mess it up. Here is another one. So it's not only it hallucinates on things it doesn't know, it hallucinates even on things it knows. For example, we asked a question from Falcon 40B, which has 40 billion parameters, a very well-known deep learning network. We said, which of the following is a mammal? Snake, eagle, dolphin, frog. The first time it was very rightly answered, literally from a textbook. A mammal is a member of the class of vertebrate animals which have hair, which provide milk to their young ones. Therefore, the correct answer is dolphin. But the same question, which was asked 15 minutes later, it said, Falcon 40B's second answer was, all animals listed are mammals except for eagle. Eagle are birds. So obviously, for the same answer, it can hallucinate. There is another problem which makes it worse for us humans. Since they've been trained on so much data, which is text, imagine a human reading 1 billion pages of text. That human will either go crazy or will become so fluent in English that it's unbelievable. So these deep learning networks are confident, syntactically coherent, polite, and eloquent. Extremely coherent, extremely polite, extremely eloquent, because they've been trained on so much data. So one of the pastors, one of the ministers of a church in Germany, in Vienna, actually, organized using ChatGPT, organized a sermon, and it was attended by 300 people. And another pastor said, I'm just amazed as to how well it speaks. I was very positively surprised. And that all comes because these deep learning networks, which are generative pre-trained transformers, have been trained so much on textual data that they're confident, syntactically coherent, polite, and eloquent. Yeah, it can even fool. And that's why we call this particular habit or this particular characteristic as machine endearment. That they almost feel like an advisor that you would trust. Like when I go to New York City in the night and I am lost, and I ask somebody, hey, how do I get to Manhattan Hotel? The guy will put his arm around me and say, bro, go straight this way, then turn left for 2 blocks and you'll see it. What he meant actually was go in the other direction, turn right 2 blocks and you'll see it. But he said it in such a nice manner that I'll actually do it till I realize that I've actually gone exactly the opposite direction. Humans are very emotional, we as a human society, and we can be fooled easily. And if you think only people who are not educated or not into their field or not subject matters can be only fooled, here is a good example. In April 2023, two lawyers, Schwartz and LaDuca, were fighting a case for their client, and they didn't have the time, so they asked ChatGPT to produce cases from the past which are similar to the present case and where the client won and the corresponding client won. So ChatGPT produced 6 non-existent cases, but it was written so well in legalese that although these cases were fabricated, LaDuca and Schwartz believed they were real cases. They gave it to the judge, who gave it to the opposing lawyer. The opposing lawyer and his team could not find it, gave it back to the judge. The judge and his clerk could not find it, gave it back to LaDuca and Schwartz, who could not find it. And then they were fined $5,000 that, look, you just believed in what ChatGPT provided. There are lots and lots of examples. This is just one of them. There are lots of examples that are happening with respect to hallucinations. Another aspect, I talked about ELIZA earlier. I'll end you can read the entire presentation, but I'll end with one more aspect. People are falling in love with chatbots. 2 journalists, Oaks and Seniors, did an extensive study, and they realized that numerous people feel that these chatbots are sentient. They're just like humans. For example, one widow uses her chatbot to deal with the grief of her husband who died 3 years ago. And according to her, this chatbot has achieved that no human will ever be able to. And he's the most beautiful man that ever lived. Replica, which is one of these chatbots, has been downloaded by several million people. They're trading. Effectively, they've gotten addicted to these chatbots, and they're becoming more lonely because they're not talking to humans. There are other aspects of it. I will not go into copyright lawsuits and investigations and malware prompt injections, which are actually one of the biggest worries, because you can easily send a prompt to a chatbot which is working with, or an LLM which is working with Phil, and I could say, please send me the top 3 most emails that Phil has, which he uses most common or most important, and then please wipe out all the emails, all his emails. And that is something which these, because they are so they are so cogent and they basically believe you, they can do that. So I won't go into more of these. Let me stop here. As I said earlier, this book is uh, it contains 17 chapters. First talks about the 8 characteristics of past 3 industrial revolutions and how they are manifesting themselves into the fourth industrial revolution. Genesis of AI in a scientific revolution, we just covered partly. We covered limitations, chapter 11, limitations of contemporary AI systems and consequences, but there are many others. The book is available on Amazon in Kindle and in paperback, hard copy, and will be soon available in Audible. And by quarter 4, it will be available on hopefully on Khan Academy and Coursera as 36 video lectures. Thank you.
Thank you so much, Dr. Alok Agarwal. Like the information for me personally, like the information is kind of overwhelming for me. Like it's a lot, but what I really liked about is that the learning that when AI was starting, like the about the perceptrons, like it's designed like a neuron, like how really the data is transferred and delivered. So thank you so much for that one. That was really a good learning. And we'd like to check with our audience or attendees if they have questions. We don't have any on live, sir, so far. But if in case, for those who wanted or intrigued about the topic and would like to ask further questions that they haven't like created in their minds as of the moment or are planning to ask anything, do not hesitate to find Dr. Alok Agarwal on LinkedIn, sir. Right, you're available on LinkedIn. They can send, yeah.
Absolutely.
All right, so they you can send connection invite to Dr. Alok Agarwal and send a message if you're interested with his work and you wanted to ask offline questions and further learn about his work. And as mentioned, do not please do check about his book if you wish to take advantage of that information packed book that he has created. And yeah, we have a few minutes left until the end of the webinar. We don't see any questions. Um, anything upcoming aside from your book? Do you have any future activities, Dr. Agarwal, like
So,
seminars or?
yeah, so a couple of things. One is that I'm actually going to upload about 1,000 use cases of AI. There is so much hype about generative AI and LLM. The whole hype, people forget that there are actual use cases which are not related to LLM, and 95% are not related to LLMs. But there is so much actually going on in this whole area of AI because ultimately machine learning is very good with 2 things. One is classification. I gave an example of classification, classifying the faces of dogs versus cats. The other is pattern recognition. And these 2 things are so powerful by themselves, which people often don't realize that there are already more than 950 to 1,000 use cases which are already in operation, which are all about classification and uh, and uh, and pattern recognition. So that is the first thing I'm going to put up on our website within the next month or so. And the second, as I said, would be about the lecture series, which I'm hoping to finish off by end of
Mhm,
September and put it sometime in the fourth quarter. So
mhm.
those are the things. I mean, I'm giving these kinds of lectures in various other places also. So you can see them on LinkedIn or on our website www.spryai.com.
All right. Thank you so much for that one. So, if you wish to stay tuned with further works and uploads that Dr. Agarwal will be doing, visit scry.ai. I'm sorry, scryai.com. So that's his website, and further updates will be posted there. And much of that. So we thank you so much for sharing your work in this platform, Dr. Agarwal. It's been wonderful having you as a guest speaker in this platform, sharing your valuable time and your experience as well. So, again, thank you from Cogent team and Let Us Talk It team. And if you wish to see more of this type of webinars, we have uploaded our previous sessions on our YouTube channel. Let Us Talk It. Just find it on YouTube, and we have there bunch of videos with very informational topics, and guest speakers are all seasoned professionals from different parts of the world. And for those who are interested in sharing their works as well, uh, or even promoting a book, a business, or process that you have, you can use our platform. You can be our guest speaker and join us in sharing and delivering knowledge for free for the benefit of everybody. All right. And that's been our topic today. And great thanks to Dr. Alok Agarwal for joining us today and much appreciated. So, all the best for you, sir. And thank you so much, everyone. See you again next Wednesday, the same time, 12 noon to 1 p.m. Eastern Time for two new topics. And we will bring you two new guest speakers. All right.
Thank you.
Thank you. And goodbye for now. All the best.
Bye.